Okay, hello everyone. Uh, Welcome to the lecture. And can you please confirm if you can see my screen and hear me clearly? Okay, thank you for confirming. So last time we were talking about why the memory mapped IO devices they create problems by not following the abstraction for memory. So the basic idea was like, let me just quickly recap this slide. So the basic idea is that what is the like expected memory behavior whenever you whenever you perform a read operation, you get the latest or most recent data written to the given address. So that data is returned, and whenever you perform the write operation, so the whatever value you provide, data you provide is written at the given address, a given memory location, right? The memory mapped IO devices, they break this model. Why? Because they have registers, and when you write values to those registers, so it is not like only the data is written into those registers, but as a result of the value written into those registers or those locations, some actions are also taken. So I gave you an example of this from your uh, what is this? Assembly programming and machine organization course where you are writing, for example, if you write some particular bits in the let's say the data direction register of a port, so you are not only writing data into the direction register, but you are also the configuring it so it takes some effect. So for example, it configures the direction of the port whether as an input port or as output port, right? So this is not the same as the behavior of a passive memory device. So also the other thing is like, when you read from memory mapped IO devices, so for example, their registers, so maybe they will always return you the fixed value instead of like giving you the most recent value written to those registers. So uh, and this is a problem. So that's why to handle the problem of memory mapped IO devices, what is the problem that they do not follow the typical memory behavior. So that's why what the solution that is proposed is that other than that the designers have defined different cache behaviors, and then they assign those cache behaviors to different memory regions. And one of those memory region can be the memory mapped IO devices. So what is a memory mapped IO devices? So memory mapped IO devices is like, if you don't know about it, so memory mapped device, how it works, like it appears to your processor, or it appears to your processor, it appears to your software, and like any other memory location. But what happens is that any data you write to that memory location, it actually goes to your IO device, or any data you read from that memory location means that you are reading that data from the IO device. So to the software, it looks like as a regular memory location, but actually it is not a memory location. It is the data is written to or read from an IO device, or more specifically, some registers of the IO device. So so what are those different cache behaviors? So one of that is uncacheable. So maybe it more makes more sense if I skip all these. Let me start with from this one, the write back memory behavior, cache behavior. Why I'm starting with this one? Because this is the standard cache behavior. Like when we are not, let's say you don't have any problem created by the IO devices, memory mapped IO devices, which mean they exactly give you the same behavior, or they show the same behavior as any other memory location. Then in that case, we don't need these other memory behaviors which are listed here, and I will explain them in a minute. So we don't need them, and we will use the default behavior, which is write back. So what is meant by this write back behavior, cache behavior? Okay. Before I explain this slide, if you have any questions about caching behaviors, please write them in the chat box. Okay. And if you don't have questions at this time point, you can wait. And when I'm like done with the slide at the end, I will. And if you have any questions when we are going through the slide, you can write your questions. I will take care of them at the end of the slide. So, what is write back behavior? So, write back behavior means that any memory region or a range of addresses which follows this behavior or which shows this behavior. So if you read the data from that memory location into the from that memory location, then that data will be cached. So its copy will be placed in L3. Let's say if you have three level hierarchy and L3 is inclusive. So when you read the data from the memory, the data will be a copy will be placed in L3 and then in L2 and then in L1 and then it will be provided to your logical core or to your pipeline, right? And the other thing is that the speculative reads are allowed on the data, which is for which we have defined or for which we have specified the write back cache behavior. Also, reordering is allowed. So, by this time point, I expect you to already know what is speculative reads. Speculative reads mean that, for example, if you are reading the instructions from a memory location for which the caching behavior is write back, and the instruction which you read is, let's say, a branching instruction. So you don't wait for that branch to be resolved. You do the prediction and you based on the based on the based on the prediction result, the next instruction sequence is fetched from the predicted path, right? So that is known as speculative reads. So speculative read is allowed. Similarly, reordering is also allowed. So instructions which you are reading from the memory region having the back caching behavior. So reordering is allowed. Reordering, we have seen already what is reordering, what is meant by reordering, which it means like reordering the execution of the instructions, right? Reordering the execution of the, reordering the data accesses, memory accesses, right? So the how in this case how the writes are handled. So whenever you update a data, so that data is updated in cache and then flushed later. Flushed later mean that uh, when, for example, there is no more space in the cache. Let's say there is no more space in L1 and you need to flush it or move it to the lower memory like L2, then it will be moved to L2 at that time point, right? And coherence is enforced, which means that if you have multiple cores sharing, let's say L3, so coherence is enforced on the memory region or on the memory locations for which the defined caching behavior is write back. What is the use case? Normal DRAM data. Okay. Are there any? Okay, let me have a look. So ASCII inputs from a keyboard would be in a memory location uh, that is accessible by the cache. Mm, uh, mm, it depends, but based on the behavior of the data, I would expect it depends. When I say what does it mean when I say it depends? It depends mean like you need to define the caching behavior for that IO device in this case the keyboard, right? But then which caching behavior you will select? I will based on the fact that uh, the keys or the data you are entering is not, maybe it is not repetitive. Let's say if I'm simply writing I'm pressing all the keys from A to Z, A B C D up to Z, right? So if there is no it seems like there will be no reuse. So if there is no reuse based on that pattern, I can say okay, make it uncacheable, right? So every time, for example, read the data from the keyboard and put it in the L1, but provide it to the core without making any copy in L3 or L2 or L1, right? But as I said, again, it depends upon your nature of the data, right? So, for example, if you are reading data, let's say from some um, if you are reading data from some network or from some online file, and the data in that file is repetitive, which you are going to like use multiple time. When I say repetitive, it's mean that there is locality. So then it will be not a good idea to define its caching behavior as uncacheable. So again, it depends upon the nature of the data. Okay, so any question about write back behavior at this time point? So write back is like default or standard behavior of the data. Okay. If no questions about write back, now let's go to the first behavior, which was uncacheable, right? So this when you define this behavior uncacheable for a region of memory locations or for a range of memory locations, so it's mean that any data which will be read from that memory and brought into the core or into the pipeline or fetched, that data will not be cached. So a copy will not be created in L3, L2, or L1. Speculative reads will not be allowed, right? And again, you know by this time what is meant by speculative read, and reordering of the instructions which are accessing the data from a memory region having uncacheable behavior. Reordering of those instruction is also not allowed, right? And how writer handles. So if you want to like update the data, so you send the right signal or right request direct to the bus, direct to the system bus. So what does it mean? Let me show you. So let me draw. Let's say you have a core here, and typically, I mean, the L1 and L2, they are inside the core, but here for our ease of visibility, I am just depicting them outside the core, right? And here then you have L3, and then maybe L3 is shared with another core, right? And at the lowest level, you have memory, right? So in memory, you can define ranges, right? Let's say I define this range to have uncacheable behavior, right? Now, if any data is, if let's say the application or process, let's say process A running at core 0, it issues a read request from the address which falls within this range. So since I have defined uncacheable behavior for this range, what will happen? Let's say that data which is needed is X. So this data will not be copied in L3, not or not be copied in L2 or L1. It will be directly fetched and placed into uh, will be provided directly to the pipeline. Okay, so it will be directly fetched and provided to the pipeline. So it will be not cached anywhere. And when you need to, let's say, update X, yeah, like you have, let's say you are doing the instruction X is equal to X plus 2, right? So here you are first reading it from the memory and then adding 2 to it and putting it back in the memory, right? So it's mean now you need to write it. So when you need to write it, so it doesn't you it since you have no copy created in L1, L2, and L3. So what you do is that you send a write request to the system bus. So what is the system bus? It is the bus which connects your cache hierarchy with your memory, right? So you directly send a request, write request to the system bus without creating any copies in L1, L2, and L3 because the data is uncacheable. So what are the examples? Like use case, so device registers are order sensitive IO. So why it makes sense to use to not cache, for example, the device registers. Again, if let me go to one node. So because let's say I have the using the system bus, I have also connected an IO device here. I have an IO device connected. Let's say IO device one, right? So this IO device, internal to it are some registers. Let's say some control register A, right? Control register A. Now let me change the color. Now just assume that uh, if for this control register A, the defined cache behavior was not uncacheable but was write back. Okay. So if it was write back, and if I wanted, if my my process A wants to write something, or my software wants to write some data, some bit pattern into this control register A, so what will it do? It will first issue a request for it, right? So what will happen that this value of like it has some address, right? Let's say the address is, I don't know, maybe address X, right? So what will happen that this data will be brought first into the memory hierarchy. Like you have here, uh, let me, you have here a copy of CRA created here. I'm assuming that L3 is inclusive, right? And then it will be provided to the core, right? And then core will update it. So when you will update it, it will be updated here in L1, right? Let me change again the color. So it will become here CRA. It will be updated only in L1, but the updated value will not be propagated. Why? Because here we are saying that defined cache behavior is write back. Since the updated value is not propagated down to L2 and L3, so what will happen? That the actual value the new value CRA, which will not actually reach the register itself, right? So since the new value will not reach the register itself, the your IO device will not be programmed, right? If I give you the same example which I gave you earlier, like for example, configuring the mode of a IO port on your microcontroller, right? So if the value you are writing is updated in L1 but not actually in the register, so your port will not be configured. Its mode, whether as input or output port, will not be updated, right? That is like a reason we that is a like reason or a use case where we can use the uncacheable behavior. If now we do the uncacheable behavior, now when you do the update is not performed in the cache hierarchy. It is performed directly to the sent directly to the bus, and then the destination register, for example, in our case, CRA register, control register, it will be updated, right? The other cache behavior is write combining. So in let me first okay, let's follow the same pattern. Let's first understand what happens, how this cache behavior is different, caching behavior is different from uncacheable. So in write combining, we still do not cache the data in the cache hierarchy like L1, L2, or L3, but we have write buffers, okay, or store buffers. They are known as store buffers. So what we do is that uh, again, uh, we still want data to be directly written into the destination. Like for example, if it is a memory map device, so and it has if it is a memory map device and it has its internal buffer which can hold the data, we still want data to be written there, right? But it can be more expensive if you, for example, write down each byte or each cache line one by one. So what uh, designer do that, instead of caching it, they have they have a store buffer. So they put the data in the store buffer, and once the buffer is full, then they write the whole data, whole buffer to the memory mapped device. Again, let me try to explain it. using one note here. So it is same in the same to the uncacheable behavior in the sense that and to keep the thing simple, I am using only L1. Okay, I'm not using L2 and L3 because it just like the idea is same. I don't want to draw the whole figure. Okay, and here you, let's say you have memory, and since this is system bus, you also have an IO device. Okay, so in unca in what was the name of this cache behavior? Let me check again. Yeah, right combining. So in case of then right combining, what you do is like uh, if let's say you have some data which is produced by the core, right? By a process A running on core 0. And since it is not cached, so if you need to write, you need to write it into the destination address, right? Now that destination address can be a memory, or it can be like an IO device. However, let's say your process first generates 1 byte, right? Uh, 1 byte of data, and you send it down from like core 0, and it goes to the bus, and it goes to the bus and then to the IO device, whatever is the destination address. It can be, as I said, memory address or an IO device, right? And then so this was your byte 1 or byte 0, let's say, and then you generate another byte. So you send the second byte, and then you send the third byte, and then you send the fourth byte. Now the problem is that every time you perform a write on the system bus, you are paying the latency, right? And the unit of sending the data on the system bus is a cache line, right? So 64 bytes. So even like, for example, when you are saying that I want to update a single byte, still you are paying the same latency, or you are occupying the same amount of resources which you will need to write a 64 byte amount of data, right? So what do people do that to avoid this? And you still don't want to pull this data in the L1. So what to do? So inside the core, if you have a store buffer, you have a store buffer, right? And then what you do is that when the process A produces B0, you don't send it to the system bus, you put it in the store buffer. And then B1, it is also placed in the store buffer, right? So you wait until the buffer is full. The size of, let's say, the store buffer is 1 cache line, right? So when 1 cache line is ready, so then you send down to the on the system bus to reach the destination address, which can be memory or an IO device. So the purpose is to basically uh, avoid the contention on the system bus, and not how to say, and to avoid the wastage of resource wastage. Okay. One thing you need to keep in mind is that this optimization of write combining is possible only when these bytes which you are producing in sequence, like B0, B1, like which are produced after one another, B0, B1, B2, they are they belong they you are writing them to the continuous address range, which mean the first byte that is produced is at address, let's say, I'm just making up number, 64. Then the next byte that is produced is 65 at address 65. The next one is at address 66. So basically they are aligned, right? So they belong to the same cache line of 64 byte size. Okay, let me finish this, then I will take your question. So in this caching behavior, still data is not cached, but it is buffered. It is buffered in store buffer. Speculative reads are allowed, and reordering is also allowed. reordering of the instructions which are accessing those memory locations, right? And similarly, reordering of the speculative execution of the instructions uh, uh, which are fetched from the memory range to whom we have allocated or assigned the right combining cache behavior. So how are writes handled? I explained writes merged into line transactions, cache line transactions. So use cases, for example, when you are working on a frame buffer or video frames which need high throughput. So in your video frames, like when, let's say your process is reading a video frame or it is reading a array of pixels of a photo or picture. Now, though those pixels are most probably like next to each other, so they belong to the same cache line. So it doesn't make sense to like process each pixel and then send it to the system bus one by one. So it is like wastage of the resource. That's why you can first fill the buffer of one cache line, 64 bytes, and then send it to the system bus to write on the destination address. Okay, let me check if there is any question. Uh, okay. What are writes in write combining memory? Why are writes in write combining memory stored in a buffer instead of being written directly to the memory? Okay, I just answered it, and another student also answered your question. Improves perform by only doing reads first, then writes once the buffer is full. Yeah, that's correct. Okay. Write through. So write through, it is the cache behavior where you use this cache behavior where the data is read frequently but not updated frequently. Okay, so for example, again it depends upon like nature of the data, right? So that's why what you do here is that you cache the data, you create the copy when you bring it from the memory, you create the copy in the cache hierarchy, like let's say L3, L2, and L1, right? So as a result, what happens that if you are reading the same data for multiple times, it is placed closer to the core, like let's say in L1. So after the first read, it becomes less expensive because for the future or subsequent reads, you don't need to go down to the memory, right? So, but when you need to update the data, so you don't update that data in the caches. You update that data down to the directly by going down to the memory. Okay, so writes go to the cache and buses, but misses don't fill the cache. Oh, sorry. What I was explaining, it was non-temporal, right? Sorry, that is not the case here. So write through basically mean that when you update the data, it is updated in the caches, and it is also updated all the way down to the memory. So if you update it, it will be updated in L1, in L2, in L3, and in the final lowest level, which is the memory, right? And what is the use case that large device memories? The case where you have IO devices with large memories are from where you are reading a lot of data, but you are not updating frequently. So this is used to avoid cache pollution. So how it is different from write back, which we have covered earlier. So let me explain it. So in write back, if you so the common thing between write back and write through in both caching behavior is that whenever you bring a data from the memory, a copy is created in L3, L2, and L1. However, the difference is that in write back, when you update the data, it is updated in only in L1, right? It will be copied back to an L2 only if, let's say, in future you need to bring in more data in L1 and there is no space, so eviction happens, and one of the cache line is evicted and placed in the L2. So only in that case. But if there is no, like, the initial update happens only in L1, right? But in uh, write through, what happens that, let's say if you want to update the data, you brought the data, let's say data Y, you brought the data when you read it, you brought it to to all the levels of hierarchy, and when you update it, let's say I'm updating it to Y in red color, so it will be updated in L1, it will be updated in L2, it will be updated in L3, and it will be written also in the memory. Okay. So that is different from write back. In write back, it would have been updated only at L1. And then it would have been pushed into L2 or L3 only in future when there is no more space in L1. Okay, so why is write through better for avoiding uh, cache pollution? Okay, anyone who want to answer this? Why is write through better for avoiding cache pollution? So compare it with the write back. So in the case of write back, it can happen that you uh, have some data like let me select this color. So for example, you have some data Y which is updated in let me select different color to indicate that. So let's say you updated Y in L1, right? But your L2 has an older or stale version of the Y, right? So from the like perspective, once where is the most recent version or valid version? It is in L1. But in L2, you are occupying the space to hold the older version of Y, which is shown here in the blue color, right? So now this cache has become polluted from the angle of validity of data. You are still holding the space, but the data which is placed in that space, the occupied space, is not valid anymore, right? So it makes your L2 polluted in the same way it makes your L3 polluted, right? But if in case of write through, when you are updating it at L1, you are also updating it at L2, and you are also updating it at L3. So yes, you are occupying the space, but the data that is placed in the occupied space is the valid data. So like you are not polluting the cache. You contain the valid data in those cache hierarchies, right? Okay. So can anybody tell me what is like downside of write through the write through caching behavior?
It's excuse me, it's resource intensive, so you want to use it for like read heavy stuff.
Read heavy. Yeah, that's true. That's true. But one more thing is like if you look if I simply try to answer the same thing which you said or explain it from different angle is that every time when I'm updating the data, I need to write it in L1 and L2, L3, and L and the memory. So I am like how many writes I am performing? I am performing like as compared to write back, I am performing three more writes, and those writes are in the lower levels. As I move lower in the hierarchy, it becomes more expensive to write. Why? Because it takes more time to write, right? To update the data. So, like in terms of latency, it becomes more expensive. It is good in saving the space or keeping or not polluting the caches, but then it is bad from the perspective of latency. Okay, so we have already covered write back, and the last one is write protected caching behavior. So, uh, so this is the case where we want our data to be cached, but cached only for the reading access. So if you want to update the data, you cannot update it in the cache. You must go down and update it in the memory. Why? Because the data covered by write protecting cache behavior doesn't provide or is not backed by the cache coherence. So So this is for the buffers for devices without coherence, are like uh, which are not covered by the coherence protocol. Remember why we need the coherence protocol? Because we want that the data which is shared among, let's say, multiple cores, and if a single core or one of them updates the data, we want all other participants to become aware of the update, and we want the updated data to be made available to them, right? So, but if we say that we are using some devices which have internal buffers to hold the data, and that data is not uh, covered by the coherence protocol, it's mean that we cannot share the data among multiple cores with the right permissions. We can allow them to read. We can, like, each one of them have a copy in their private L1 or L2 read the data. So, but they are not allowed to modify, because if any one of them and a single participant if modifies it, it's mean other will not be able to have an access to the updated variant, and the data is not covered by the coherence protocol. So, uh, what does it mean? Then how we perform the update? So to perform the update, every write must goes to the bus, which means every write must be performed in the memory only. So this is different because this approach is different. Write protected is different from uncacheable or write combining. How? Because in uncacheable and write combining, you cannot cache the data even only for read purpose. Here you allow the data to be cached, but only for read purpose. However, you are not allowed to perform the write operation on those cached lines. Is it clear to everyone? Like how write protected mode is, our cache behavior is different from uncacheable or write combining. So it the basic difference is that it allows caching the data in those caches like L1, L2, and L3, but only for read purposes. Whenever any core wants to update the data, the write must go directly into the memory without creating any updated copy in L1, L2, and L3. Okay. Any questions? Okay, now why we were talking about these caching behaviors? Because we said that the write write back is the caching behavior which is compatible with the memory abstraction we talked about in start when we started discussing this paper, right? But the memory map devices, they do not follow that memory abstraction, or they do not follow the behavior of the like a passive memory. So that's why we need to have other caching behaviors which are more suitable for the memory devices, depending upon uh, what is the use case, right? So, but once we know these caching behavior, we need to assign them to the memory ranges, right? So for example, let's say if you say like I'm just making up a number, address range from 100 to 200 is reserved for memory devices uh, who have buffers, but which do not support the coherence of their data, right? Coherence protocol for their data. So for that range, I need to use the write protected caching behavior for all the memory devices mapped in the range 100 to 200, right? Similarly, let's say I have another set of memory map devices which I want to use the uncacheable caching behavior, right? So how then I can do that? For like, how can I assign the caching behavior? So to configure the caching behavior, there are four different levels. Uh, Either you can set a caching behavior globally mean at that behavior will be applied the processor wide. All the memory accesses which are performed by the processor, they will follow that cache behavior, right? The other way is that you can divide the memory into the ranges, and then for each range you can specify the desired caching behavior. The third option is that uh, for a given memory range for which you have defined the cache behavior, let's say here, now that memory range is accessed by processes, right? In form of pages, like, which mean that basically that the memory range can be divided into multiple pages, right? One memory range can be possibly divided into multiple pages. So what if you want to say, I don't want to use the uh, uh, same caching behavior for the whole memory range. Maybe let's say there are four pages, page 0, 1, 2, and 3, and caching behavior defined for that range is, let's say, uncacheable. But later on you want to say, okay, I want to keep uncacheable behavior for page 0, 1, and 2, but for page 3 I want to change it to, let's say, write through caching behavior, right? So for that you can use the page table attributes. So like it gives you more control or more fine granularity of for defining the caching behavior. And page table bits, they are actually another way of doing the same thing which I just explained here. So I will explain all these three or four approaches in little bit more detail. But here on the right side, what you see is that at the top most you have the coarse granularity, and at the bottom most you have the fine granularity of defining the cache behavior for a given memory region, right? So the global control using CR0 register, uh, so you can set the bits like cache disable and not write through bits to apply the caching behavior to the entire processor. So which basically mean that all any memory accesses performed by the processor will follow the caching behavior which is defined by setting the bits. Like for example, if you are saying caching is disabled, so it's mean that it will be assumed that caching is not active, and all the memory accesses, for example, all the data that is read will be directly read from the memory, and without creating any copy in the caches will be provided to the to your pipeline. Similarly, any data that will be produced will be directly written into the memory, right? So, and this not write through basically mean like whenever the data is updated, it will be updated following the write back policy. Okay. But then again, it will be applied for all the memory accesses. Whatever policy you select, it will be applied to all the accesses performed by the processor. So these bits, they act as global switches that override the caching behavior everywhere, right? So if you say not cacheable or cache disabled, so it's mean all the memory accesses will be cache disabled. If you say not write through, then all the memory accesses will be not write through. Okay, so the next option is like you partition the memory. Let me check the time, guys. Okay, let me at least complete this slide. So next option is like, for example, so the first option, this one was like if I select this bit equal to 1 in the control register, so any, and this is, let's say, memory here. So any access into the memory will follow the not write through policy, right? But this is less flexible. Let's say later on I want to provide the flexibility. For example, for certain kind of data, I want to use, let's say, uncacheable policy, and for another, let's say, I want to use write through, and for another region, I want to use, let's say, write back, right? So how can I do that? So for that, what I can do is that this option give me the possibility to partition the memory into the regions with caching types, and these caching types are then defined for the fixed in the like legacy systems. The older systems you had the fixed ranges, but now in the like modern systems or Intel 64, you have variable ranges of the memory, right? So, and how those ranges are defined by using a base register and a mask. So this is just like the concept is similar like what we have seen earlier. I don't know, like base plus offset register. If you remember when we were talking about execution context. So the idea is similar that you define a base plus mask, which basically tells you the range. Like for example, base is this register, and mask will define the range, like how region of the memory on which you want to apply a particular caching behavior, right? Third option is now just like I said earlier, let's say you have this particular region of for which you had defined the write back policy. So this region can be defined, let's say it is equal to 64 kilobyte, right? If it is 64 kilobyte, how many pages we will have in this 64 kilobyte region? We will have 16 pages, right? If one page is a 4 kilobyte, right? So let's say you will have page 0 here, and you have at the bottom I'm just writing P15, right? Now let's say you want to modify the caching behavior for page number 7, right? How will you do that? By setting the page attribute table. So basically what happened is that your operating system stores 8 entries in a 64-bit model specific register, and then your page table entry, it has a 3-bit index, which gives you the pointer to the caching behavior. So like let's say this is your model specific register, right? And in this model specific register you have 8 entries. I cannot draw 8. So from the page table, remember what was the job of the page table? To convert a virtual address into the physical address. Other than holding the physical address, it also, if you remember, it also holds some other data. For example, if a page table entry is valid, if a page table is writable, if page table entry or the page which is pointed by the page table entry is writable or not, right? It also has information. It also have 3 extra bits here, and these 3 bits provide you an entry into this model specific register, specific field in the model specific register, which actually gives you the like for example, this entry is, let's say, for uncacheable behavior. This one is, let's say, for write through. The next one is, let's say, for write back. So based on those 3 bits, you determine what is the cache behavior for this particular page, right? Okay, and page table bits, these are another ways of saying the same thing. Like you can have these bits enabled or disabled to define like whether you want to uh, uh, whether you want to disable the page level caching. You, for example, you don't want the whole page to be cached. So whenever any data is read from that by a process or a software from that page, and that page is marked as page level cache disable, it's mean any data that is read will not be copied in L1, L2, or L3, right? And similarly, for example, you can say page level write through. So any data that is updated for that page, it should be updated in all the cache level hierarchy, like L1, L2, L3, and in the memory. Okay. Let's see if there are any questions. When would an OS disable caching globally? Okay, it's a very nice question. So one example is in the case where, for example, let's say you are using non-volatile memory. What is non-volatile memory? What is volatile memory? Volatile memory is like your DRAM, right? Uh, uh, DRAM is volatile, so when you remove the power, your data from the DRAM is also removed, right? It is lost. So non-volatile memory is where data is stored permanently, right? So if, let's say, you are making updates in the non-volatile memory, and you don't want to end up in a situation where your updates are not yet reached to the memory, but they are in cache. You have made updates on the data, but those updates are in the cache, but not yet reached in the memory. And let's say you lost the power. So what will happen? Since your caches are volatile, the data will be lost, right? So in that situation, what we want is like, okay, I want to disable caching for the data which I am writing to the non-volatile memory, uh, so that I can directly write the data down to the non-volatile memory. So even like if I'm sure that if I send an update, that update goes directly to the non-volatile memory without being stored temporarily in the cache, so that I can avoid the situation where where the power is lost, and as a result my data is also lost, because all the time I'm saying I'm disabling the caching and I want the data to directly reach into the non-volatile memory. What could happen to system performance if caching is disabled using CR0? Anyone who want to answer this one? What could happen to system performance if caching is disabled using CR0? Come on, guys, it's your chance to answer and then put it in your class participation form and get points.
Would it reduce performance?
Yeah, but why? Yeah, it will reduce the performance, but the reason is like, where was the question? Yeah. So because then you will not be able to benefit from the data locality, right? Uh, for example, if let's say if you have an array of data, like let's say if consisting of 1,000 elements, and you are accessing each element 10 times, right? In a sequence. I don't know, maybe you are repeatedly incrementing it or doing some operation, right? So if there is no caching, then every time in those 10 accesses, you will need to go down to the memory and access the data from the memory, right? So it will drastically reduce your performance. Does making something uncacheable actually stop timing side channels, or just move it from caching timing to memory timing? Actually, yeah, that's a like good question again. Uh, if you if you like maybe it can be a trivial way of like naive way of uh, at, at least mitigating those attacks which rely on exploiting the data left behind in caches or cache timing attacks. So but then it will be it can mitigate those attacks, but then it will incur huge performance degradation. Okay, there are other questions. I'm guessing we'll pronounce okay without confusion slow because we have to fetch from. Okay, I think other students are trying to answer the questions, right? Yeah. So okay, let me stop here because we have a presentation today. Uh, who is presenting today? Can you please uh,
Yes, that
respond?
would be me, Kid Martinez.
Gaden. Okay, then okay. Okay, so let me allow to share your screen. Let me allow you to share the screen. I think I have enabled. Let me stop share. Okay. I'm unmuting myself. You can start the presentation. And again, if you have questions, you can put them in the chat box. Kaden, is it fine if I record your presentation?
Yes, that's fine.
Thank you.
All right. Please let me know if you can see my screen.
Yes, I can. I can see.
Okay, the orientation is good as well.
Yeah, it's good. Yeah,
Okay.
it's readable.
Okay. Today, I will be discussing Intel SGX Explained sections 5.9 to 6.2, beginning with the motivations and contributions. The first section I will be covering today was written to introduce and explain the idea of the launch enclave present within SGX. The latter two discuss in detail how the implementation of SGX is handled at the most basic hardware level. These three sections together show us the beginning of Intel SGX from a design standpoint, while explaining how exactly the alterations affect the processor itself and its host machine. Beginning with section 5.9, as I said, is SGX enclave launch control. So the launch enclave in the approval process. SGX requires an approval given by the launch enclave before it actually begins. The reasons for this are largely detrimental as it enforces software licensing. The launch enclave distributes einit tokens to serve as the approval to allow SGX to execute. These tokens are also used for licensing that forces Intel to be an intermediary. So the launch enclave and software licensing creates a binding agreement with Intel and is only meaningful if if it enforces this between the user of SGX and Intel themselves. These are invasive as some software can enforce a given launch control process, enforcing the aforementioned Intel intermediary relationship. Enclaves are unable to damage the host computer as they are isolated in ring 3. However, this also means that antivirus is somewhat ineffective as it cannot see what is happening inside of the enclave. Because they are isolated from all outside software, this means that bad actors can use generic loaders to bypass the antivirus and execute payloads outside the enclave after they undergo attestation within the enclave, somewhat like a Trojan, but a bit more complicated than that. And on the figure on the right, we can just see the computations that occur when an einit token is generated. Section 6.1 begins the SGX implementation overview, and Section 6 as a whole is the SGX analysis. Section 6.1 focuses on the modifications required for SGX. Implementing SGX has a low impact on the chip hardware design. Small modifications are needed to the execution cores in the page mishandler, the PMH. The only modification to the PMH hardware that is absolutely necessary to implement SGX is developing an ability to trigger the microcode assist for all address translations when a logical processor is in enclave mode, or when the physical address produced by the PageWalker FSN matches the processor reserved memory range. So this just has to do with allowing the address translation that we've talked about in some of the prior classes to actually occur by making these changes inside of the page mishandler. Modifications are made to the uncore components to stop unauthorized direct memory access, which we'll talk about more in the next couple slides. Uncore components are caches, memory controllers, and things of that nature for reference. All SGX instructions are also implemented at the microcode level, including asynchronous exits and the initialization process, which occurs after launch enclaves have begun their enforcement of the policy. Intel documentation shows some of the microcode registers present in an enclave page map entry. And this is what we can see on the right, the fields in an EPCM entry. So the SGX microcode set up entries in the source address decoder, SAD, in the Uncore C boxes, and in the target address decoder in the integrated memory controller. So that's where some of these instructions are going to come, as you can see in the fields in the EPCM entry and what they do. Finally, section 6.2, as I alluded to earlier, is SGX's memory access protection, which is one of the primary draws of SGX as a hardware mechanism, and one of the main reasons why we'd like to use it. So SGX protects against software attacks using memory checks. These checks ensure that currently running software cannot access memory outside of the PRM range. SGX implements the access control logic in this figure. And SGX security checks also come after any attribute checks, the attribute checks occurring in the launch. We can see here that one of the things that it hinges on is, of course, it must be executing within the enclave code. Then does it have a physical address in the PRM? I'm tracing down the right side of the branches as well. And this is where we see yes. And here is the big one. If you see physical address in the EPC, if not, it'll throw a page fault. And then if yes, it'll continue reading forward. So virtual addresses inside the enclave's memory range must always translate into physical EPC addresses. Otherwise, it just will throw a page fault. An EPC page must only be accessed by the code of enclave who owns the page, and some pages cannot be accessed at all by the software. So an enclave's EPC pages must be accessed using the virtual address associated with them when they were allocated to the enclave. Pages with SGX internal structures like SACS, TCS, or VAs must only be accessed by the microcode and cannot be accessed by any software inside the enclave or out. All implementations of SGX's security checks entail adding a pair of memory type range registers to the page mishandler. The registers added to the page mishandler are the secure enclave range registers, SERR, which allow the enabling of SGX on a logical processor that initializes the SERR to the values of the protected memory range registers, PMRR, that being the second one that is added. Continue forward. Some of the strengths, weaknesses, and suggestions that I had with this paper. The strengths are that the explanations of details behind Intel SGX's implementation and standpoint were great. It did a great job of explaining the more esoteric details behind SGX from an implementation and design standpoint. References to previous sections of the paper helped to keep it concise, as this was the part where we actually begin to see what is happening underneath the hood. They were talked about in depth that helped make it concise and easily readable while building on prior concepts now in the context of SGX. One of the weaknesses, of which there were many, is that a lot of details were inferred from patents and other technical intel documents, specifically with launch enclaves having a lot of information obfuscated and also just inferred. They kind of assumed what was happening based on some of the other patents that they had come together and cross-referenced, but it also made it difficult to just know like what is actually happening and affected the transparency. An ongoing issue that I've had with the paper is that some sections felt like acronym soup. So, I mean, even in my presentation, I was throwing around a lot of different acronyms, and it's difficult to know what exactly is being talked about without referencing back and affects the overall readability. Mentions of topics that were not directly related to SGX or affected by SGX were present in the launch enclave section, specifically about Intel's monopoly, the net neutrality agreement, and how the launch enclaves can be compared to verified boot. And while this information is helpful, it's largely supplemental and I believe could have been removed. Some of the suggestions also felt unnecessary in that same vein. The suggestions made for the page mishandler improvements were most end, which makes their inclusion feel redundant, as it talked about how some of the optimizations that can be made for the page mishandler help to speed up time whenever there is actually like a page miss, but those are relatively infrequent. So the optimization that you're getting doesn't really affect or improve your performance in the long run. Finally, my two suggestions are to cut some of the talk on irrelevant pieces of hardware or just things that weren't explicitly relevant to SGX as a whole. And finally, to reduce the number of proposed suggestions or improvements to SGX and focus on the explanation. Now, I will take any questions that we have.
Okay. Thank you, Kaden, for your presentation. Can we go back to the slide where you had this control flow diagram? I think it is
Yes, that would be
third last slide.
this one. Yes.
Yeah. Yeah, let me just go through it.
Yeah, I was mainly talking about what's happening in the right branch. If you see kind of in the middle, the physical address to the EPC is what allows us to continue forward as they must translate into physical EPC addresses.
Okay, I don't have a question. I just wanted to have a look at the figure.
Okay. I
Okay.
see there's 3 questions in the chat, so I'm gonna go ahead and answer those if that's all right. If you didn't have any other things you wanted me to move to.
No, go ahead.
Okay. So the first is, how could the LE be removed since it is detrimental? The LE being the launch enclave, for those of you who may have forgotten. So it could be removed by using antivirus as a monitor. I know I mentioned earlier that antivirus doesn't necessarily play well, but that's because the launch enclave actually exists in the first place. So if we use antivirus as a monitor, it would have the enclaves being policed by intelligent antivirus that functions a little bit different than some of the implementations that were popular at the time of the writing of this paper. So it would record and filter the I/O performed by Enclave software and detect malicious software according to the actions that it performs, rather than according to the bit patterns in its code, which is primarily how antivirus functions. It's just a pattern recognition. It looks for things that are out of place or things that have been like repeating over and over and over again that don't really make sense in the context of that software. So it'd just be a different approach to antivirus, could make it so that the launch enclave could just be removed, no longer enforce those rather unsavory intermediary connections with Intel.
Okay, I
Did
have a
that answer your
follow-up
question?
question.
Yes.
Why a launching? So L is for launching the enclave, right?
Yeah.
So why it is detrimental in what sense? What do you
So
mean
it's
by when you say it
detrimental.
is det? Okay, go
So
ahead.
detrimental in the way that it kind of enforces an agreement with Intel being an intermediary between the software that you are running, essentially forcing you like knowing kind of what you have going on inside your enclave, if that makes sense. It just establishes like a connection with them for attestation and stuff, and you might not want
So it is
Intel to be
detrimental in
involved
the sense
whatsoever.
that it takes long time for the process to complete, right? For launching the
Yes,
enclave.
and also just might be somewhat of an invasion of privacy by having Intel be involved in a way that you might not want them to be.
So, okay, so I get that, like because you need to do to perform the attestation, so it takes time.
Mhm.
But then, what is the role of antivirus in that context? I mean, how it has to do anything with reducing the latency of attestation?
So in the paper, it's not so much talking about performance saving. I don't know if actually having just an antivirus that's already there, like what how resource intensive they are. But the software licensing agreements is primarily what I'm focusing on when I talk about the how detrimental LEs are. You might not want your a software licensing agreement to be created with Intel with the software that you're using inside of an enclave if it's like your personal intellectual property, if that makes sense. So less so on the front of performance and more so on just data privacy and keeping what you have to yourself instead of sharing it with Intel, which is forced with launch enclaves. Does that answer your question?
Uh, yeah, okay, okay, we can move to the next question.
Okay. What are some advantages of SGX modifications having a low overhead? And one advantage is that since the modifications are either self-contained modules or within the microcode itself, they support a much higher development speed than having to create entirely new circuitry, so build a new processor, and then that would have the updates. So this means that new updates can come out frequently and add new features or patch any issues that may arise.
Okay, so what is the next question? Why doesn't SGX use the memory encryption engine for protection? I think SGX uses the memory encryption engine for protection, doesn't it?
So the SGX actually doesn't use the MEE for protection because the MEE sits in the processor's memory controller, which is at the edge of the on-chip memory hierarchy, even below the caches. So it can't protect an enclave's memory from software attacks that are occurring inside.
So you are saying it is not using memory encryption engine.
It doesn't, no.
So how then it encrypts the memory accesses, the data that is sent to the memory, how it encrypts it?
I think it talked just about using the uh, memory isolation so that that way it can't really be accessed by anything. I don't know about, I think the encryption just maybe happens with the attestation. I do know that it doesn't use the MEE though.
Okay. Anyone who want to respond to this? I mean, we have a question here or a confusion here. Anyone who want to clarify it? My understanding is that there is an on-chip. When I say on-chip, it's mean on the same chip where you have the processor. On the same chip, you have the module which is responsible for encrypting all the accesses going to the memory and decrypting all the accesses coming from the all the data which is read from back from the memory into the chip. So yeah, but I agree with your point. If the memory encryption engine you are saying is on the memory chip and not on the processor chip, then we cannot trust it. That's correct.
Yeah, yeah, that's what the paper said.
Okay, so is it like before the arrival of the Intel SGX, the memory encryption engine was on the memory chip? And I'm just trying to understand. So clarify if it is, correct me if it is not wrong. So before the arrival of the Intel SGX, the memory encryption engine was on the memory chip. And
Mhm.
then with the Intel SGX, they provided, I'm assuming they provided a support to hardware support to encrypt the data on the chip and then send it off the chip to the memory chip. When I say on chip,
Yes,
it's
yeah, it was just it's a configuration. Yeah, I believe that's the kind of timeline. So now with if you want to use an Intel SGX chips, you can't use the MEE because of some of the other that was like one of the minimal hardware changes that was required in order to
yeah.
get it to run.
Okay, okay. Because yeah, okay. Because that is what I remember from like my understanding of Intel SGX. Okay. So
Yes.
anything else? Any other questions? No? Okay, thank you, Kaden, for your presentation.
Okay, I'm gonna
And
go ahead and stop sharing.
yeah, now is the time for your class participation form. Let me give you the code, access code, and I will also extend the time by 5 minutes so that you can complete it. Okay. So I have shared the access code. I am online until on my side until 4:25. I'm online. Okay. So if you have any question or any difficulty, let me know.